Our group for this lab was Jonathan, Stefan, and myself, Drew. The objectives of this lab and the specifications needed in this lab. The goal of this lab was to create a model and a controller for an electric car system for the company Solco, which was getting into electric car space. The model must be able to control the speed of the wheels of the car, and then we want to reach desired speeds and locations precisely without having overshoot, error, and having minimal settling times. For the controller process of the lab, the first labs create a mathematical model measuring certain constants of the system. Using a motor and a flywheel, we were able to create a model and measure the motor constants and different friction constants as well. We then used those measured values to create transfer functions, which then we could test in other labs with different controllers to find which would meet our specifications.
Using resources such as MATLAB to meet specifications, we landed on the PID controller as given. We also included an extra filter to filter out extra noise. We arrived at this controller by first finding the open loop transfer function needed for this system, then using this transfer function, finding values needed to spin the disk at a certain speed, then using the final controller to meet the requirements. To mimic the effects of disturbances instead of true disturbances such as wind, an idealized extra voltage input was used. We also assumed a perfect sensor and ideal components. The PD controllers, or proportional derivative controllers, has pros that are easy to implement, improved stability, faster response. The cons are its steady state error may exist, more high frequency noise. For proportional integral controllers, the pros are zero steady state error, reduced noise sensitivity, and the cons are slower response and it may be harder to tune. For a PID controller, or a proportional integral derivative controller, the pros are the best of both worlds, the best of the proportional derivative and the proportional integral controllers. The cons may be that its careful tuning is required and it may be harder to implement. So therefore, based on the requirements given, the best controller for this application is the PID controller. We want a steady system with a reduced noise sensitivity and a fast response, and improved stability, and zero error.
As a result of this lab examining how we can model the desired speeds and location achievement for electric cars, this could also be used for other practical purposes. One, as such, is for autonomous vehicles that can be tuned with similar PID controllers to have extremely small or no error, thus making transportation faster and safer by reducing traffic fatalities or congestion. Said systems can also be applied to critical surgeries that will reduce medical injury, thus lowering the need for malpractice insurance or even reducing lawsuits. Related to medical, said controllers could be used to enable the creation of better artificial limbs or even more practical medical devices such as respirators or artificial organs that will have more reliability and less error as a result of the properties discussed beforehand.